Hi. Hey, so I guess we are doing lab 10 because that's the only thing that's left. So we want to decompose x to the n into small problems. We actually had hello. Okay, let me plug in the projector. Do you live in Chestnut? Fine.
No.
Okay. Are you downtown or did you like commute?
Oh, close.
Oh, okay.
Why ask?
Just curious.
Because I don't know garbage bin.
Hmm?
Is it a toner
Oh, I see.
for the printers?
I
I
see.
really like red zero.
Yeah. There's like some stuff. Yeah.
I think I can open it and see how it works.
I'm not sure if that's gonna work.
I don't think so. That's why it's open.
Yeah. All right. Uh, projecting. Yeah. Okay. So we are doing problem one. And we want to decompose x to the n. So there's multiple ways of doing it. The easiest way that's like the same as the factorial is to just say x to the n is x times x to the n minus 1, right? So the recursive function here would be like this. So we'll just say if n is equal to 0, x to the 0 is equal to 1. Otherwise, we do x times x to the n minus 1. So again, the usual thing, we call power as its own helper function. So assuming that this computes x to the n minus 1, this is x to the n just because of the math. So, okay. So we now want to compute power to 3, so 2 to the power of 3. So basically, we call power we'll just do it. That's not. So power is 2, 0, and this returns 1. And this is 2, 1. So power to 1 calls power to 0, and power to 0 returns 1. And then power to 1 was called by power to 2. And that was called by power to 3. So power to 1, we can go back and see what it computes. So power to 0, we already decided returns 1. So power to 1 is going to be here. And this is, so x is 2. And then it's going to be 2 times power to 0. So for that reason, power to 1 is going to return 2 times 1. And that means that power to 2 is going to return 2 times 1. Because power to 1 returns 2 times 1, and power to 2 returns this 2 times power to 1. And this means that this returns 2 times 2 times 2 times 1. So that's power 2 to the 3. All right. Okay. So we want to sum up the digits of a number. Sorry about this. So for example, we want to, we want to compute 1 plus 2 plus 3 here. So what's the recursive step here? So if I have a number and I want the sum of the digits, one way to do it is to say is sum of digits of so 4, 3, 5, 3, 4 plus 1. Right? So I'm saying compute the sum of those digits and add this digit. And that's going to be the sum of the entire thing. So there was like other ways of setting it up. I could say, well, like do 4 plus the sum of those digits, but it would not be as convenient. So let's do it. So what I'm going to say is, okay, like if the number is just 0, then the sum of the digits is 0. And then I'm going to say, so what's the last digit? The last digit is n mod 10, right? So the last digit is the remainder of the division by 0. And then how do I get the sum of those digits? Well, I do n divided by 10. So so you divide this by 10 with integer division, you get this part without the last digit. And I'm just saying sum up those digits. And that's it. And again, kind of the design here is you don't usually think like bottom up, like what do I do? I need the sum of the digits. You just think, okay, like how do I figure out how to call the function as its own helper? Okay. So wait. Oh, yeah. How did that happen? Okay. So we are now doing times, which I guess was the original problem too, because this seems easier. So we want A times B. So the idea is we want to use this fact. So A times B is this much. So A times B minus 1, and then add in one more A. Okay. So anything multiplied by 0 is 0. And then we just use the formula. So we say A times B minus 1, and then add an A, and that's A times B. Again, just the recursive step plus leap of faith, right? So the recursive step is just like the math just says like A times B is equal to this much. That's just the math. And we're just calling times as its own help. And then the base case as well, like anything times 0 is 0. So that's going to work. All right. So now we want linear search. So here's a way. So we're basically saying, okay, like we want to see the index of not what I wanted. Wait, did I want it true or false? Or yeah, we want the index. So if the length of L is 1, then we are saying, okay, the answer is 0, right? Because So basically what we're saying is like if it's not there, then we return none. So if the length of the list is 0, then it's definitely not there. So we return none. If the length is 1, we check. And the location is either 0 in the list of length 0, or if it's not there, then it's not. So now we need the recursive step. And how do we do the recursive step? Well, so we'll say, okay, so let's call linear search on the rest of the list. And then either this is none or it returns the result. So if it's none, then we return none because we didn't find. So we didn't find it, right? On the other hand, if it's not none, then we return 1 plus result because we have the location inside of here, but the location inside of here is like 1 less than the location inside the big list L. So I missed one more base case, which I'll incorporate here instead of this guy. Because right now what's missing is I did not check whether the answer is 0. So I'll just check. And I'll return 0 if L at 0 is target, right? Because if L at 0 is target, then the location is 0. So now that I've checked it, I can do this. Because I'm doing this, I don't need length of L equals 1, right? Because if the length of the list is 1, I'll just check is L at 0 target. If it's not target, what's going to happen is I'm going to call linear search rec on the empty list, and that's going to return none. So I'm going to return none. Make sense? All right. So that's one way of doing it. All right. We are doing interleave. So we want to interleave L1 and L2. So there are 2 lists of the same length, and we want this. So how do we do that? So here, like the math is actually like easiest to write as so the math is easiest to write in just Python. So how do I interleave? I say make L1, L1, 0, L2, 0, and then interleave the rest of the lists. So that's kind of the math, right? So if L1 is 6, 7, 8, and L2 is 1, 2, 3. So interleave L1, L2 is going to be 6, 1 plus the interleaving of 7, 8, 2, 3. Right? And that's exactly what I'm doing. I'm saying take those and then interleave the rest of the lists. All right. So I now want to do a reverse of a list in place. So that means I want to keep so I want to just like interchange all the elements in L, right? So if L is I want to make it be 8765. And one idea is I want to swap those guys. And then I also want to swap those guys. So one way of doing it, and that's kind of what the loop suggests, is keep track of the index that I'm swapping. So technically you were given the signature. So to have a default argument, you have to do something like this. So here, what we're going to do is we're going to say, okay, like if I is more than half the list, then we're done. We don't need to reverse anything. If not, then we swap Li with the corresponding element on the other end. And then we reverse the rest. Here we'll just call it. All right. So what we're saying is reverse list I, kind of the way it uses itself as a helper function is it swaps the ith element with the corresponding element on the other end. And then it says, take care of the rest. Right? Does that make sense?
Yeah.
All right. Cool. All right. So now we are doing this. So without using loops and without using print with a list, print the elements like this. So what we're doing is we're doing kind of what you did in the previous question, but in the other order. And not swapping, just printing, right? So we'll start with this zigzag. So what does this do? So it prints the first element of the list, the last element of the list, and then it says, just keep going, right? So print element number 2 and element number 2 from the other end, and then element number 3 and element number 2 the other end, right? So that's like L at 0, and then L at -1, and L at 1, L at -2, and so on, right? So that's what it prints. So, okay. So what we want to do here is we want to do the same thing, except in a different order. So here we start with printing this, and then eventually we'll print L at 0, L at 10-1. So one way to think about it is that's the same trick as when we swapped the order in which we printed and called, and it printed the list in reverse instead. And that's like actually like all it is. So
It's like a task problem. Well, this is exactly should be given or
I mean, it depends.
oh,
So I mean, like, you know, like it's like like obviously it would be like a harder problem if it were not given. But like it's also, like it's not as if there's like lots of those kinds of ideas floating around. This is like, like I like literally remember this from like my exam, like it says in the handout, like maybe we come up with something that's like that, but like also maybe not. Like it's, but again, kind of when you're designing problems, sometimes you want to give a difficult problem. Sometimes you want to give an easier problem. So sometimes you give context and that makes it easier. Sometimes you don't give context and that makes it harder. It's also the case that like everyone's seen it and has done it in the lab. So that's like a different complication. Okay, so let's first run zigzag 1. No. So let's see why this is not working. So we have if length of L is equal to 0, then we just print nothing. If length of L is equal to 1, we print L at 0. Otherwise, we print L0, L1, and we call zigzag 1 minus 1. Should work. Print L. Okay, so the issue is that we keep calling on the empty list. So why is it that we keep calling on the empty list? That's because I only want to call this if I'm here. So that was like an indentation, and that was just an indentation issue. So that's like this. So we have 162, 16, 25, 34. So we have a spacing issue. Yeah. So we have a spacing issue. So that is going to be like this. So, okay. So that's like this. So now we want to reverse it. And like one way to think about it, and that's like a hacky way of thinking about it, but you just change the order in which you call those. And that reverses the process. So the explanation for what's going on is like this. So what we want to do is we want to print 3, 4, and then 2, 5, and then 1, 6. Right? So in order to do this, what we're going to say is print the inner zigzag for this guy, and then print 1, 6. Right? So that's the picture here is zigzag, and then first element, last element. And that's what we're doing here, right? We're saying zigzag on the inner list, and then 1, 6. Right? So like in order to print like 3, 4, 2, 5, 1, 6, we're saying first print 2, 5, 3, 4, and then print 1, 6. Right? And that's what we're doing here. So like we're saying in line 108, 2, 5, 3, 4. And 3, 4, 2, 5 rather, and then 1, 6. And that's what we're doing here. So do the inner list and then do 1, 6. So, like the trick I'll say is like kind of like the vibe is, well, like if you switch the order in which you call and print, then it kind of reverses. But obviously, like it's just like set up so that it works out. It's not like guaranteed that like if you just go off the vibe, it's gonna work. But in this case, it does, right? Okay. There are project 3. So what did they do here? Oh, so this is just the splitting. So what we want to do is we want to say there is a splitter. So the splitter is so the splitter here is what 3, 6. So that means that like anytime you see a 3 or you see a 6, you split. So here's one way of doing this. So what I'm going to do is I'm just going to go through the list L, and I'm going to replace all the splitters with one kind of splitter. So if it's a string, then you can do something else. But with the list, what I'll do is I'll just make my splitter placeholder thing. And it doesn't matter. I'll just call it like this guy. And then I'll go through the list L and I'll replace anything that's a splitter with this guy. So I'm going to say, we'll copy L just so that they don't mess up the original L. And then I'll say for I range length copy L. So if it's a splitter, then I'll say copy Li is the splitter placeholder. So now instead of every splitter, I have my special splitter placeholder thing. I'm just doing it so that it's analogous with what you do with the strings. So if L initially was this, 3, 6, then I replace the 3 and the 6 with splitter placeholder. Where's my 6? Oh, here. Right? So now this is like not the most elegant thing to do. I'm just doing it so that it's analogous with what you do with strings. So now what I'll do is I have my result. And I'll just go through the list L and I'll build up the current sublist and then append it to the result. So basically, like have a running current sublist, build it up. So build up the sublist 1, 2. And then if I encounter splitter placeholder, I just append it to the result. and I reset current sublist to the empty. And then again, I build up current sublist. And then if I encounter a splitter, I append the sublist again. So this is much easier to do with the helper function because like with strings, you have like dot split and you have dot replace that are built in. So dot split, if you give it one splitter, it'll just call it. So replace is going to do basically this thing, but automatically. So here I'm kind of just doing it without the built-in functions because like with lists, that's not really available. All right. Questions? Cool. Oh my God. Was I not sharing for a long time?
No, you were. I was able to see it on my end.
Well, I guess it was like in the back.
No, like I could see screens
Sorry,
still.
Nicholas, you're saying something?
No, I could see your screen still.
Yeah. I know. So like it was like, okay. Oh, you can. Okay.
Yeah, on my side I could see it
Oh,
even
okay.
on the computer screen.
Okay. That's good.
Yeah.
Hey, okay. Well, I'm at 4% battery, so I think this is it. Okay. All right. Okay. See ya.